Hello, I am Guilherme Lourenço de Toledo, and this work was developed in collaboration with Professor Ricardo Marcondes Marcacini at the University of São Paulo. I will present our work, Transfer Learning with Joint Fine-Tuning for Multimodal Sentiment Analysis. The sentiment analysis task is related to the identification of a sentiment polarity through data, such as text or images. Although most methods focus on textual analysis, there has been a massive movement to multimodal sentiment analysis. Complex applications require a large amount of data. A crucial step in multimodal learning pipeline is to obtain sufficient multimodal data for training, along with the challenge of aligning modalities. State-of-the-art models have been using datasets with text paired with images for classification. CLIP is one example of these approaches. The results are very promising, but the need for multimodal pre-training became computationally extensive. In this work, instead of looking for performance improvements, we decided to take a step back and prioritize efficiency. Thus, we raised the question: how to fine-tune different pre-trained unimodal models considering a multimodal objective for sentiment analysis tasks? We introduced a joint fine-tuning approach for these models, allowing both of them to fine-tune as a single loss function during the training step along with an attention method for a modality fusion. Our architecture represents a simple and effective approach for multimodal sentiment analysis. At the top of the architecture, there are two encoders equivalent to unimodal pre-trained models on uncorrelated data. It is important to note that this can be any unimodal architecture. This approach provides flexibility for the task. The encoder's embeddings are then projected into a linear space with same dimension and then concatenated. The concatenation is passed through a multi-head attention layer followed by a feed-forward network. This is a crucial step for multimodal fusion. The attention mechanism is able to combine modalities and identify the relevant features from both modalities. Note that, at the bottom of the architecture, the gradient for one single loss function is used to update the parameters of the whole model, including both encoders. This is what we call joint fine-tuning. For our experiments, we evaluated 6 different architectures in 2 image plus text datasets proposed for sentiment analysis using tenfold cross-validation. The MVSA dataset contains pairs of images and texts collected from Twitter and manually annotated. Our MVSA 1.2K represents a subset of the original dataset. We select the samples where there was an agreement between annotators regarding the labels. We also reduced it to balance the class's distribution. The hateful memes contains over 10,000 memes labeled as hateful or not hateful. The samples are composed by images and texts, and we use it as a special case of sentiment analysis. We decided to use 2 unimodal architectures for the datasets in order to compare the unimodal and multimodal performance. We also tested these models along with a simple concatenation in order to get multimodal embedding. Their generated embedding was fed into a SVM and a feed-forward network. As a state-of-the-art competitor for our approach, we use CLIP, which explores a multimodal pre-training and representation by maximizing the cosine similarity between pairs of images and texts in order to find the best alignment between the 2 modalities. At last, we tested our approach, which was already shown, using ResNet 50 and DistilBERT as encoders. We decided to use AUC scores as the main evaluation metric. Analyzing the performance results, it is notable that CLIP has the best scores among the evaluated methods. On the other hand, our approach achieved competitive results with a much simpler strategy. Additionally, we could use any pre-trained unimodal model as encoders. As for the parameters comparison, it is clear that the pre-training cost of our strategy is way lower than CLIP, which makes our approach more accessible and efficient. We can also put both tables in comparison and conclude that our efficiency gain is worth the slight reduction in performance. In conclusion to the work, we have shown a simpler, flexible, competitive, and accessible alternative for state-of-the-art multimodal models. We also proposed an effective extension of the concatenation strategy via attention mechanisms, which can be used as an efficient baseline for multimodal classification. We have also shown that this approach is competitive to CLIP, a state-of-the-art model for image and text classification. When we put both results in balance, the high parameter reduction becomes more relevant than the slightly inferior results over score metrics. As for future works, We look forward to managing extensive evaluation of this approach, considering different models as encoders along with different datasets for multimodal classification. We also want to incorporate an explainability model as a strategy to identify the impact that each modality has on classification. This is my presentation on our paper. Thank you for your time.